deductive reasoning. So, first of all, we've learned about inductive reasoning. So why can't we just stick with inductive reasoning? What is it? And what's the problem if we're trying to prove a conjecture with inductive reasoning? What is inductive reasoning? What is it? Well, but what is inductive reasoning? First, let's say what it is. Describe inductive reasoning. I wish we had written this down in our notes in a previous class so we could refer to it right now when we can't think of it. Yes, Amanda?
Inductive reasoning is saying that something is true because every instance you notice something like that, it's true.
Perfect. That's exactly what it is. Your observation says this is the way something works, so that's the way it's always going to work. You notice the pattern, so you assume it's true for everything. So why can't we use that to prove conjectures? Sounds good to me. Why not?
Because, if all the schnauzers you see are gray, there might be schnauzers that's white that you've never noticed, and you can easily be discouraged.
Such an awesome example. So, yeah, every schnauzer I've ever seen is gray, so does that mean they all are? I don't know. Right? Maybe not. So unless you check every single case, you can't say it's necessarily true. Yeah?
If you grew up in a padded asylum with a straight jacket, you'd say all jackets are brown and all rooms are white.
Yes, and all the jackets tie in the back, right? Yeah. That's it. Your experience can be limited, and so you may not realize that there's more out there. That's a big problem, right? Yeah, one last comment. Yeah. A schnauzer's a little dog. Oh, they're so cute. Yeah, is that a little gray dog? You have a schnauzer? All right, so let's look at this. So there's the coach. Isn't that how it works? Your coach has told you that if you miss more than one practice during the week, you're not allowed to play on Saturday. You missed a practice yesterday and today, so what's going to happen?
You won't be able to play on Saturday.
Well, why not?
You'll find out their coach is bluffing.
Well, I don't know. What do you really? I don't know how many coaches actually bluff. There's many coaches. Anybody's father or mother coach? Good. I can get away with it. They're usually pretty strict, and they're pretty strict for a reason. They set rules, right? And they don't break rules. So what's going to happen if they are going to insist on this rule? You missed a practice. What's going to happen on Saturday? Not going to play. Now, is this based on observation, or is it based on a rule? Yeah.
I'd say it's based on a rule that you're coaching you up.
Absolutely. Right? Rule-based rather than observation-based. Now, if they never told you anything, and you notice this is happening, Johnny didn't show up and he's not being allowed to play. Maybe that's going to happen. That's more inductive. But if it's stated, this is the rule, then that's the rule. That's deductive reasoning. It's based on a rule. So deductive reasoning uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. Okay? It has to be stuff that's a fact, that's proven, or if it's not proven, we all agree to assume it's true. So how is this different from inductive reasoning? What's different about this? Yeah. Yeah, exactly. These are hard, fast rules and facts. So I like this kind of little picture. This always kind of tied it in for me. So inductive reasoning is, I made a few observations, so it must be true. I don't know about a case that maybe doesn't work. This is saying these are rules, hard and fast, can't be broken. Based on these things that are hard and fast and can't be broken, that's how I'm drawing my conclusion. Okay, so
This is awful powerful.
yeah, I think so too. And mathematics, remember I said mathematics deals with truth? So mathematics has a problem with inductive reasoning because what about every case? And again, real world, like science and research tends to do this because it's the best we can do, but in math we tend to do this. We won't say something is true unless we've used some form of this kind of reasoning. Okay? So let's see what else I got to say here. There's two different laws we're going to learn about in deductive reasoning. One is called the law of detachment. And this rule, it's kind of a strange rule because it seems sort of obvious. And it says if the hypothesis of a conditional statement is true, then the conclusion is true, so P applies Q. So if P is true, then Q must happen. If P is true, then Q must happen. It is true. So let's look at an example here. Mary goes to the movies every Friday and Saturday. Today is Friday. So let's convert this to a conditional. How can we write this as a conditional? Yes, ma'am.
If today is Friday, then Mary will go to the movies.
And today is Friday or Saturday, right? Because either way, she's going. So today is Friday or Saturday. Mary goes to the movies, and Mary goes to the movies. Okay, so what's the hypothesis then of this conditional statement? What's the P? Julia? Well, remember, the hypothesis is this piece, and the conclusion is this piece. So if I'm looking at this if-then statement, which is the hypothesis? Yeah, if, this part here. It's the part between the if and the then. This is like the P. So today is Friday or Saturday. That's my hypothesis. Huh?
I remember, like, our class teacher calls use if then and not.
Now you know what? Okay. Then, what's the conclusion? Yeah, take it.
Mary will go to the movies.
Yeah, Mary goes to the movies. And so far, not really different than what we've already talked about. So, is the hypothesis true? So here's my statement. Today is Friday. Is the hypothesis true? Yes. So what has to happen? What do we have no choice but the laws of logic tell us, by the law of detachment, that Mary is going to the movies. It's kind of like the obvious, but for some reason, sometimes people have a little trouble with the law of detachment because you think too hard. If the hypothesis happens, the conclusion will happen too. Yeah?
But some conjectures like that are false. If it is a Schnauzer, then it is black,
Well, then I wouldn't use that one. It's not going to be true, right?
right?
So we're trying to use one. This is a fact. Remember, we're based on
So
facts.
it only works with true conjectures.
Here's what I'm going to say. This part that I'm giving you, let's assume it's true. Okay, we have to work with the assumption that it's true. Now, if it's not true, I hear what you're saying. If it's not true, you're absolutely right. Throw it away, because then it doesn't matter. So let's just pretend or always assume these are true. But you have a very good point. If it's not true, then it doesn't really help us. Yeah.
That, there is what we conclude, just in case then the conclusion is also true.
Right, yes, and you're going to write there Mary goes to the movies. It means the same kind of thing. Okay. So let's apply this law of detachment. I don't think these are on your notes, but let's think about it. Okay, what can we conclude? When it rains, I use an umbrella. So we're going to assume that this is a true statement. It doesn't really help us, the law of detachment, unless I know I have a fact. So I have a fact. It is raining. What can we conclude by the law of detachment? I'm going to use an umbrella. So the idea is if the hypothesis comes true, the conclusion has to come true. If I wear garlic, a vampire will not attack me. Now I know it's ridiculous, but we're going to assume it's true for the law of logic example that we're doing. If this is a true statement, and I am wearing garlic, what has to happen?
Well, garlic attracts werewolves.
A vampire? No.
Carry a silver spoon.
I can only work with facts, people.
Wait, so vampires are real?
The fact like this.
werewolves are?
There used to be a show called Dragnet, right? Just the facts, ma'am. That's it. I can't say, well, what if this happened? I don't know. All I know is this. That's all I got. Okay, now this is kind of more what police work does. So they use a lot of deductive reasoning, or they should, if they really want to convict somebody. So here we go. If the accused suspect has a valid alibi, then the police will not hold him. The crime occurred at 9:32 a.m. The suspect's place of business confirms that he was working with 22 other people from 7 a.m. to 4 p.m. on the same day. So what should the detective conclude deductively?
What was alibis false?
That's not what we're asked to do. We're saying here, these are the facts, ma'am. This is what we know. What can the detective conclude? Ali, why not? No, I don't know if we can conclude that. What does my if say? What is the rule here? It doesn't say he didn't kill him. It just says, if the I'm drawing this line here. If the suspect has a valid alibi, then the police will not hold him. It doesn't necessarily mean he didn't do it. It just means what? They can't hold him,
Well,
right?
it could not be a valid alibi. It could be saying that he was working with 22 other people somewhere in between 7 a.m. and 4 p.m.
Now we have this word confirm, right? You can't now, excuse me. If I'm giving you facts here, I see that word confirm, I'm working with facts. If you were a detective and you had this, and you said, well, I think they're lying, this, that, and the other, it's a very difficult case. You have a confirmation. Yes?
Well, what if his business is
Is in
like
it.
a crime?
Yeah.
Wouldn't a
And
crime?
his place of work is a dark alley.
No, but
Listen,
Evan.
you guys should
Evan,
all be detectives.
It
All I
doesn't
know
say,
is,
it could be saying that he was working there.
but it doesn't
somewhere
say that.
between 7 to 4.
We can only, listen, you guys have these wonderful imaginations, you read way too many of these books and watch way too many movies. However, we can only go with what it says. And if it says that he is confirmed to have been somewhere between 7 and 4 p.m., the police cannot hold him. That's all it says. Alrighty. More. The law of syllogism is if P, then Q is true. You have a true statement. You have another true statement, if Q, then R. That's also true. So you can conclude that P and R is also true. Now these little dots here, see those? You may not have seen those before. This is math shorthand for the word therefore. So if you see those three little dots, it's because I don't feel like writing therefore. So if P then Q is true, if Q then R is true, therefore P then R is true. Let's look at it in the notation here. It might be a little bit easier to see it. So if P implies Q and Q implies R, they're both true statements, then P implies R. Does this remind anybody of something they've seen before? Yeah, what do you think, Julia? The transitive property of equality, remember that?
Yeah.
Right, if A equals B and B equals C, then A equals C. It's a lot like that.
We've never used that.
Oh, you will be using it this year. We will be using it. I'm glad you remembered. So P implies Q and Q implies R, then we can kind of cut out the middleman. Here's an example. If Rick takes chemistry this year, then Jesse will be Rick's lab partner. If Jesse is Rick's lab partner, then Rick will get an A in chemistry. Oh, all right, so let's look at these statements that we have. So here's like the first statement I'm seeing, if then. What's the hypothesis here? What's my if? What condition has to be true, Evan? Okay, so if Rick takes chemistry this year. What's the conclusion to that particular conditional? Does it?
Jesse will be like a good father.
Great, okay, that's one statement. I see another statement as well. There's a second conditional. What's the hypothesis of that one? Really? Good. Now we have a conclusion to that one, which is what? Rick will get an A in chemistry. It doesn't say, does it? Okay, so I can see my hypothesis and conclusion for both the conditional thoughts here. So what is my new conclusion? So if Rick takes chemistry this year, what can we conclude? Jacob?
We're gonna do it.
Rick will get an A.
What kind of that?
So we can kind of rewrite this side. If Rick takes chemistry here, then Rick will get an A. We can, because the logic says, because this will happen, and then if this condition becomes true, that happens, we can't help it. So that is the law of syllogism. Question? Question?
I don't know.
Is it relevant or is it,
It's relevant.
Okay, yeah.
You can use it to make an entirely complicated thing.
You absolutely can.
Where the beginning logic has nothing to do whatsoever with the end
Now,
logic.
did somebody, I can't remember this class, somebody said the story of the give a mouse a cookie?
Yeah.
Oh.
That's like one big giant law syllogism, and I forget how it ends, but it's like some like crazy story, right? That's law syllogism. That book is law syllogism.
If you give a mouse a cookie, he'll want a cookie.
It's kind of circular reasoning, isn't it?
I have the book.
Uh-oh. Okay, so let's look at some examples of law syllogism. When it rains, I use an umbrella. When I carry an umbrella, I don't get wet.
What
When it rains, I won't get wet, right?
what if lightning strikes your umbrella and you get electrocuted?
Okay, I can only go with the facts.
And then you're done.
Oh, yeah.
Yeah.
I think you
that's
get
what
wet
I
'cause
do.
you
I
look
think
at
they-
Yeah,
When I take the umbrella-
roll with this, okay? Right? So what does this mean? This means that, okay, that's fine. So when it rains, I won't get wet. Okay, if I wear, this is again, we're kind of taking the same things, but we're applying law of syllogism. If I wear garlic, a vampire will not attack me. If a vampire will not attack me, I will not die. So
You
what
don't
is
die.
What? Yeah. What's the statement that I can say here? Cut out the middle piece. Yeah.
If I wear garlic,
Go ahead, Joseph.
if I wear garlic, I will not die.
Yeah.
To anything?
She's really
You,
weird.
now, you know, you lose the context here, and you get rid of the vampire.
You will
part.
never die.
Die.
Oh,
You will not die by
So you
vampire.
animal.
Right.
It's the philosopher's garlic.
Yes. So, again, you're losing kind of why not gets lost here, but it's a true statement because of that. All right, now this again, more like a real life example, sort of. So in a recreational basketball league, if a player receives two technical fouls in a game, then the player is ejected from the game. If you eject a player from a game, then they have to sit out the following game. So what's some kind of conclusions we can draw here from this using the law syllogism? What do you think?
If a player gets two technical fouls in a game, the player has to sit out the following.
Okay. So it's kind of an unwritten rule, but it makes perfectly logical sense. So if a player gets two technical fouls in a game, then he has to sit out. Okay, make sense? All right. So let's see. Now I've got some statements here, and we have to figure out, is it detachment or is it syllogism that we're using? Let's see how much we're picking up here. All right, so if Dr. Klein is well rested for a surgical procedure, then she operates with precision. Dr. Klein gets plenty of sleep to prepare for today's operation. So first of all, what can we conclude here? What's the conclusion we can draw? Julie, what do you think? Huh? She won't? She will. She will operate with precision, because what is true? She got plenty of sleep, so she is well rested, therefore she will operate with precision. Is this syllogism or detachment? Detachment.
I sincerely hope that she is asleep now that they open heart surgery. What?
Okay? So we kind of look at what we got here, draw a conclusion, and then why are we drawing that conclusion? So let's see, if we don't make any stops, then we'll make it to the stadium by 12:30 p.m. If we make it to the stadium by that time, then we should be in time to see the kickoff. So, Amanda, what can I conclude here?
If we don't make any stops, then we should be in time to see the kickoff.
Excellent. And which law of logic did you use?
Syllogism, the more fun one.
This is the more fun one. Oh, okay. But yes, it's like a transitive property. Right? Great. Okay, now this, again, sometimes they're not as obvious. Even when firefighters follow all relevant safety procedures, if they enter a burning building, then there's significant danger involved. And a group of firefighters enter a burning warehouse to look for people. So what is the logical conclusion here and why? Jacob?
There's significant danger involved,
Why?
because even if they enter a burning building, then there's significant danger involved.
Right, because they're doing, see there's like extra stuff here that doesn't really apply, so you kind of have to analyze these a little bit. Okay, wait, here is the hypothesis, and here is the conclusion. Did the hypothesis happen? Yes. What can I conclude? That, by which law? Detachment. Store manager knows that if tomorrow's sale is not advertised in the newspaper, then the store will lose money. If the newspaper does not receive the order for the advertisement soon enough, then they'll not be able to put it in tomorrow's paper. Now be careful. Now, because this is how we speak. Don't always necessarily speak in the logical order. So look at that a little bit. What can we conclude? What do you think, Gary?
We can conclude that if the newspaper does not receive the order for advertisement soon enough, the store will lose money.
Wow. How'd you started with this when you went up here. How come?
Because it says they will not be able to send tomorrow's paper, and then the top sentence says it's not advertised in the paper or something.
Yeah, I mean, she was very careful to figure out what's the hypothesis and conclusion of each of these statements and matched it up properly. Because, right, the conclusion of one has to match the hypothesis of the other. In this case, kind of that first one came second. And so she was very careful with this. So do you see that? Because they said if they don't put it in the paper over here, it's not advertised in the paper, that matches this one. So she's absolutely right. By which law now?
It is the law of syllogism.
Right? So if the newspaper doesn't receive the order, the store will lose money. So we're making these conclusions. Now we make these kind of logical jumps all the time, but by kind of looking for it, you become better at making logical arguments. Alrighty. So inductive and deductive reasoning actually do work together. Inductive reasoning is still important because inductive reasoning is how we make conjectures. For the most part, inductive reasoning is how we make conjectures. However, we prove conjectures by using deductive reasoning. Do we have time here? I may come back to this, but I just want to make sure I get through the lesson. We're running a little behind here. There's a little practice on the back here. So go ahead and on page 2, see if you can first of all decide, indicate whether the law of detachment or syllogism has been used. Like what conclusion can you draw? And then, so write them down. Okay, write them down and then we'll talk about it. And then the bottom one, decide if inductive reasoning is used. What's the question? No, I'm skipping that just because I'm running out of time. So go to page 2. I think most of us are kind of, got at least most of this done. What do you think? I said what's going to happen here is you're going to wind up setting the brake by the law of detachment because you did park on a hill. So therefore your conclusion must come true. This next one looks certainly like syllogism because one of them had a conclusion if he gets nervous, the other one had a hypothesis if he gets nervous. I'm going to cut that out. If he plays in a game, he's going to perform well. This one maybe was a little bit harder to see. To me, this looks like the law of detachment. If an object has a greater volume than equivalent mass of water, then the object will float in water. So a ball has 3 times the volume of an equivalent mass of water. Now, it sounds very complicated. It's just saying this is happening. This is true. So it must float in water. Based on fact, that's what's going to happen. Law of detachment. You diet for 3 weeks and lose 3 pounds. You conclude that you can lose 20 more pounds in the next 3 weeks. 20 weeks. Sadly, this is inductive reasoning. It doesn't work that way if anybody's ever been on a diet before. It is the last day of the month. You want to buy a new jacket because you always run out of money by the end of the month. You say, no way I'm going to be able to buy this jacket. Again, inductive reasoning. Maybe this will be the month where you save your money. Who knows? Oh, this one, what's this? You use the rise of 8.1 and the run of 2.7 between 2 points on a line to conclude that the slope of the line is 3. Now, I'm saying that's deductive. Why is that deductive? It's facts, right? We have, if you calculate slope a certain way, you will get the number that is slope. So I'm using facts. Okay, questions on these? Alrighty, let's look at sets. There used to be a time when I went to school, everything was sets. We learned about sets in elementary school, still kind of a product of new math. That's all gone. So a lot of people don't know what a set is. What is a set? Anybody know? What? I want a set. A set is simply just a collection of stuff, items, you collect things, put them together. That's a set. Right? Question?
Don't you mean an array?
I'm using more the mathematical definition of set. Arrays in programming is one way to define a set. But it is similar to an array. An element is a member of a set, something inside that set. And a subset is, it's like you take another set and it contains one or more elements of a parent set. Okay, so this all sounds hard unless you look at an example, because it's not really as hard as it sounds. Every element of a subset is contained in the parent set. And let's look at an example to kind of maybe see it a little bit better. Sets are always enclosed in curly brackets. You may remember this last year when we looked at set building notation, right? Sets are always in curly brackets. And here's some members. And in this case, my members of the set are just colors. I have a set of colors. So what's an element? Well, red's an element of that set. Green, yellow, blue. Those are elements of this set. Sometimes we give these sets letter names. In this case, I'm calling it S. I can call it a different letter name. I'll be right with you with your question. Elements of S, a subset. Well, it could be yellow, red. It could be blue, green. I've got a subset here of red, green. That would be a proper subset. You can even have all of them. That's sometimes also still considered a subset, even if it's all of them. Proper subset doesn't have all the items in it. Question on that?
In Java, sets, or what they call them arrays, are contained within square brackets.
Well, again, I don't want you to think set equals array. Not
I
necessarily.
don't get it.
It's just a collection of items. Array has a sense of order to it. Sets don't necessarily have an order, so they're not really the same thing. So I want you to kind of.
An array of strings, you can put the strings in any order.
Right, but they're not the same thing. So I want you to kind of maybe not compare it to an array. All it is like you have a bag, and in this bag I have those 4 colors. They're in there. And you can pull one out, that's called a subset. You can pull 2 out, that's a
so
subset.
an array is just organized into items 0, 1, 2, 3, and in the set it doesn't really that
Right, right. Yeah.
Would it still be a subset if, say, it was red, blue, and purple?
Well, purple is not in my original set. Great question. Purple's not in here, so it would not be a subset of this.
Okay.
So your subset has to be a member of what's in your big set. Great question. Awesome questions. Yes?
So the set has to have more than one.
A set can be empty. This is an empty set. You can have that. And we saw that last year, the set of solutions when there was no solution. Right? You can have an empty set. Now, the reason I'm bringing this up because we're going to be looking at this thing called Venn diagrams. Actually, what we're looking at are actually called Euler diagrams. Euler was a 18th century Swiss mathematician. Venn diagrams are a kind of Euler diagram. Now, you are familiar with the Euler diagram. That's this thing, right? So we're looking at kind of that and other things like it. So you have a statement. If you like oranges, then you like apples. So here is an Euler diagram of that. And let's see why. If you like oranges, if that's true, then you like apples, that will also be true. So this says, in the sea of people who like apples, there is a subset of people who also like oranges. Does everybody in here who likes oranges also like apples? Yes. So does this illustrate the picture of that conditional? Think about it. So if you like oranges, all these people who like oranges also like apples. But does everybody who like apples necessarily have to like oranges? No. And that would be the converse. If you like apples, you like oranges. I don't know if that's true. So if we look at some of these statements here, and I think on the paper here I said, what's the hypothesis? And that would be this, right? And what's the conclusion? That would be that. If you're kind of following the program, I know you guys are. So let's see if I can make a conclusion here. If Betty likes oranges, what can I conclude about Betty? So Betty's right here. She likes oranges. What else can I conclude? Yeah?
That she likes apples.
That she likes apples. And that's by the law of detachment, isn't it? What? Okay, so therefore Betty likes apples. There's my therefore yet. Bobby likes apples. So Bobby's over here.
How do we know?
Well, he could be here or he could be here. Can I draw a conclusion based on knowing that somebody likes apples? We can't, no conclusion. We don't have a logical basis for making a conclusion. He could possibly like oranges, or maybe he doesn't. So this says, if you're given the law of detachment, just because the conclusion is true, it doesn't mean that this reason happened. Maybe there's another reason why somebody likes apples, I don't know. Yes?
Well, what do you mean, like, there's no,
There's no conclusion, I can't just, no, none.
are we allowed to use one, yeah?
Sure, absolutely. Now, if I know Sally doesn't like oranges, I know she's not in here, can I make a conclusion on where she might be? She could be here, she could also be in the land of people who don't like apples or oranges, right? There's no conclusion for that either. And that's really like, an inverse statement that we got here. Yeah. That's the inverse. If you don't like oranges, then you don't like apples. You can't make that conclusion. Now, what if I know Peter doesn't like apples? He is not here, right? What can I determine? Jacob?
He doesn't like oranges.
He doesn't like oranges, right? Because if you like, if you don't like apples, you could have liked oranges. And that's a contrapositive.
She likes bananas.
You don't know that. Just the facts, sir. Just the facts, all we can do. Okay, so using these diagrams, some people can actually see it better with the diagrams. Let's see, illustrating some. So how do you say something like some butterflies are yellow and red? This is your classic Venn diagram, right? So you have yellow butterflies, you have red butterflies, there's some overlap. So this is how you can show this in a Venn diagram. Some butterflies are both yellow and red. Okay? This one's another way to look at some. Some rectangles are squares. Now notice how in the sea of rectangles, some of them are squares. So this says all squares are rectangles. It's another way of saying the same thing. It's another way to say the exact same thing based on this diagram. This one's an Euler diagram. Questions on sum? How we illustrate sum? Huh? Well, you can make a note if you want to make a note. Right, so this one we kind of have to have that overlap because some are, there's two things involved. Now, if there's no cats are gray and orange. So if you want to illustrate that, see how these circles do not touch. This Euler diagram has them completely separate. They're their own separate world. There are no cats that are both gray and orange. Illustrating these things. Okay? So let's kind of see if we can kind of draw one. So I want to illustrate conditions, and I'm going to use an Euler diagram here, that some triangles are acute, and acute. Remember what acute triangle is? The angles are less than 90. Some triangles are obtuse. One angle is more than 90. No triangle is both those things. And some acute triangles are equilateral. The sides are all the same. Now, when you want to draw this, you know what my mind immediately went to? The no. So here's the land of triangles. None of them can be acute and obtuse. So it must be that those are two separate circles, right? Because they can't be the same. So I got that. Alright. Some triangles are acute. This says that, doesn't it say some triangles are acute? I think we're doing that. Some triangles are obtuse. We're doing that. We're doing that. How do I say some acute triangles are equilateral? What would I do?
Circle overlapping acute and equilateral.
Look at that.
It's all equilateral triangles, right?
But it doesn't say, oh, wait a second, I'm backwards here. No, that's right. Some acute triangles are equilateral. Actually, this goes in here, right? Like that.
No.
Doesn't it?
No, all
Oh,
of
that's
people
backwards.
Yeah.
That's backwards. So we make the circle. We've got our land of acute triangles, right? And inside this land of acute triangles, some of them are going to be equilateral. That's better. Right? So all equilateral triangles are acute. Some acute triangles are equilateral. Whew. Now we got it. I think we got it now. And then last little bit here is, I might actually have you do some of these. Like, what can we say here? What statement can we draw from this? Yeah? Joseph?
All triangles are polygon.
All triangles are polygon. Okay. What's another way of saying the same kind of thing? Yeah? Some polygons are triangles. Yeah. If it's not a polygon, then it's not a triangle. Wow. If it's not a polygon, then it's not a triangle. Good one. Yeah.
If it's not a triangle, it's not a polygon.
If it's not a triangle, it's not a polygon.
Oh wait, no, it's not a.
Oh,
it's not
no.
a-
That one, right? It could be a pentagon, right?
Yeah.
So it could still be a polygon. Yeah, excellent. And then this one, because we're almost done here, use the diagram to determine what you can conclude. If Moby is a whale, what can I conclude? He's a mammal, right? Randy is not a whale. I can't make a conclusion there. Alex is a mammal. Right? No, that's all I know. Nothing else. How about Myrtle is not a mammal? Not a whale. And that is our Euler diagrams in a nutshell.